Operating an aircraft involves a lot of planning. If a flight is properly planned, pilots will always know what to do next if a degradation happens to the aircraft, such as an engine failure, no matter where along the flight, from brakes release for takeoff to when the aircraft stops at the destination gate. When we say planning, we mean not only flight plan, weight and balance, and other dispatch documents, but also training to handle contingencies. In this video, we will take a careful look into what may happen during a takeoff. We will be talking about performance, piloting techniques, and flight standards. And the idea behind producing this video is to provide the Embraer customers quality practical information that can help enhance the safety of their operation. The purpose of this video is to make useful information available to all operators of Embraer ERJ aircraft about what must be remembered on a takeoff. Flight safety is a combination of things: aircraft properly maintained, and crew properly informed and trained according to proper flight standards. The basic concept behind air transport operation is an engine can fail no matter when during a flight, from brake release to vacating the runway on arrival, without jeopardizing safety. Takeoff is the most critical phase. Of course, if an engine fails during takeoff, performance will be penalized. In case of two engines aircraft, the failure of one engine will mean an overall thrust reduction of 50%. Several things affect takeoff performance: air temperature, pressure altitude, runway slope, wind component along the runway, and many others. The way each of these parameters affect the takeoff performance depends on the type of engine and the type of aircraft. Take, for example, the temperature. Temperature affects the takeoff performance for two reasons. First, because the thrust delivered by the engines changes with temperature. And second, because temperature affects air density. The lower the air density, the higher the speed relative to the ground the aircraft must reach before getting airborne. Brakes have a very important effect on takeoff. Strange, isn't it? Takeoff consists of basically accelerating the aircraft to a speed which the aircraft can become airborne. So what role do the brakes play? The brakes are a key factor if the pilot decides to abort the takeoff at a high speed. As a matter of fact, the most demanding situation as far as the brake effort is concerned is when a high-speed abort at maximum takeoff weight takes place. The amount of energy that the brakes dissipate on an aborted takeoff is of the same order of magnitude as 200 heavy braking of a mid-sized car from 60 miles per hour to 0. If such situation ever happens, the brakes get extremely hot to the point that the temperature fuses in each wheel may deflate the tires. These fuses exist to prevent the tires from blowing up. ERJ 145 pilots have to check if brake temperature is within the green range prior to takeoff. If not, they must not attempt to take off, because if they do, and the need to abort it at high speed arises, the end result may quite well be landing gear fire and damage. So high brake temperature is no-go. If the aircraft is dispatched with an inoperative brake temperature sensor, then the quick turnaround weight chart in the AFM must be checked at intermediate stops to find out if time on the ground needs to be extended. Will such deflating ever happen on a landing? No, if system status is normal. Brakes are also designed to stop an aircraft on a landing at maximum landing weight, maximum certified tailwind, and maximum certified downhill slope at high density altitudes. So, can a pilot decide to abort a takeoff anytime? No. Performance calls for a V1, also known as takeoff decision speed. Actually, V1 is the maximum speed at which action to stop the aircraft can be taken. During the certification process, a speed called VEF, engine failure speed, is defined based on the test findings. VEF is the highest speed at which an engine can fail. VEF is lower than V1. So actually, the aircraft continues to accelerate from VEF until the crew takes action to abort the takeoff, V1. Time span between VEF and V1 is usually around 1 second. The performance data assumes that time plus 2 seconds at V1 before deceleration begins. It is very important that the crew be aware that V1 is not the latest point along the takeoff where an engine can fail. It is rather the latest point along the takeoff where an abort action can start. But before we go on talking about V1, we would like to emphasize that V1 is to cover engine failures cases only. It does not cover situations like, for example, blown tires. Blown tires are much less able to decelerate the aircraft than normal ones. So deciding to abort a takeoff at a speed slightly less than V1 because of blown tires can be a very bad decision leading to a runway overrun. How much before V1 can you abort due to blown tires? It is impossible to determine. So pilots must be trained to quickly decide what to do next on a takeoff because there will always be a margin for judgments. Other problems such as vibrations, warnings and fire, other than engine fire, are remote possibilities which demand decision-making in a split second. Pilot proficiency means, among other things, skill, and perhaps more importantly, ability to make quick and correct decisions. Back to V1. Care must be taken when making allowances for the time between engine failure and call-out and abort action. Excessive allowance will affect the overall takeoff distance over 35 feet negatively. The recommended practice is having the crews aware that V1 is speed for abort action, and that if they are not able to commence the abort at V1, don't commence it. One important point is, once abort is commenced, use maximum braking effort until there is safe evidence that there is no risk of a runway overrun. Improper evaluations of the remaining runway available cause accidents. If an engine failure happens after V1, what to do? There is just one thing to do. Continue takeoff. The published performance guarantees that if the takeoff technique is consistent with the published one, the aircraft will climb out safely and will overfly the opposite end of the runway or end of the clearway at a height of at least 35 feet. Aborting a takeoff at a speed above V1 is a serious mistake if the aircraft is runway limited. Around 30% of the takeoff accidents are caused by high-speed aborts. Aborting a takeoff after rotation was initiated should never be attempted. When an engine quits, the remaining thrust will be offset relative to the center line. This means that the aircraft will tend to veer to one side. The pilot is always able to counteract that. The takeoff speeds are determined to take that into account. If the aircraft is at or above the published V1, the aircraft is definitely controllable on the ground. And if the speed is equal to or above VR, then it is certainly controllable in flight. The reason is, these two speeds are respectively greater than VMCG, minimum control speed on the ground, and greater than VMCA, minimum control speed in the air. What are these two speeds? VMCG and VMCA. These speeds are determined during the flight test program as speeds above which the aircraft is directionally controllable on the ground and in flight, respectively. The takeoff must be done without the use of hand steering. The use of the steering hand wheel may cause pilot to oversteer the aircraft, resulting in possible loss of control or damage to the nose tires. The steering available through the pedals is more than enough for takeoff. As a matter of fact, the flight tests to determine VMCG are done with the nose wheel steering fully deactivated, yoke trigger pressed. However, Embraer does not recommend any unorthodox technique, such as taking off with steering deactivated. A quick but important remark. Differently from some other aircraft, the ERJ-145 does not require yoke full forward during takeoff roll to ensure directional controllability if an engine fails after V1. Suppose the aircraft has VR and has an inoperative engine. Then what to do? There is no written recipe that will make the reader proficient at takeoffs. There is no substitute for training. But we would like to remark that over-rotation is dangerous. Over-rotation may lead to a very dangerous situation, where the speed drops fast and directional and lateral control may degrade to a point where piloting the aircraft becomes very difficult. And the worst possible situation is an abnormal attitude near the ground. So care must be exercised when rotating the aircraft. Under-rotation is also undesirable. The pilots must use normal pitch rate for a liftoff, and once the aircraft gets airborne, the speed to look for is V2. If engine failure occurs after V2 is attained, reduce to V2 and climb to level off altitude. Then follow the standard profile until you reach VFS and final segment climb. If it is impossible to reach V2 after level off altitude was reached, increase speed to VFS, leveling off from the greater speed. If engine failure occurs between V2 and VFS above level off altitude, increase speed to VFS and follow the standard profile. If the engine fails above VFS, reduce the VFS and follow the climb path until you reach the altitude that defines the end of the takeoff with engine failure. That is a technique that minimizes drag. The ERJ-145 has plenty of rudder authority, and techniques, such as lowering one wing by 5 degrees, are not appropriate for the ERJ-145. What if there are obstacles ahead? What if the planned standard instrument departure requires a high climb gradient? One thing can be done for sure. The aircraft can be dispatched assuming that a contingency climb procedure, sometimes called an escape route, that is less restrictive performance-wise than a normal departure, will be used in the event of an engine failure. In that case, several measures must be taken before the flight. Air traffic management authorities must be aware of this contingency route and will coordinate other air traffic in the vicinity to avoid conflicts, should it ever be used. If this contingency route includes turns, then the performance-limited takeoff weight must take into account corrections to climb gradient due to the bank angle. V2 is valid for bank angles up to 15 degrees. Greater bank angles require a V2 correction. See the Embraer AOM for these figures. Engine failures may happen anytime. They may happen at V1 or later along the takeoff path. The takeoff performance analysis should evaluate all cases. If an engine fails, say at 700 feet, perhaps the aircraft is well into a standard instrument departure, and transitioning to a contingency climb at this point may be complicated. So, whenever there are escape routes, a decision point, whether continue on the standard departure or switch to the contingency climb, is necessary. It is always preferable to clear the obstacles in the second segment, that is, before reaching the acceleration altitude. The reason is, the gradient improvement due to flap retraction is not significant, and it takes a reasonable distance to accelerate from V2 to VFS. A takeoff at night, or in rain, or yet in bad visibility with a failed engine, demands a good deal of attention. The crew must be trained to prioritize aviating the aircraft. The thing that deserves the highest priority is to fly away from the ground at the planned speed and in a normal attitude. Once that is taken care of, then the crew can work on navigating and managing the systems. Any change in this priority, such as managing the systems before a safe height is reached, can have serious consequences to the safety of the flight. One important fact that should be addressed in training is EGPWS is becoming mainstream. It is available on most ERJ. It is a fine piece of equipment and is a great boost to flight safety. However, the crew must be aware that the terrain clearance floor logic embedded in it is not consistent with the ground clearance provided by the obstacle clearance calculation method. The obstacle clearance calculations assume a height margin of 35 feet plus 0.8% of the distance from the end of the runway to the obstacle. However, the terrain clearance floor logic in the EGPWS is different from that. This difference means that in some particular circumstances, when obstacles are overflown at reduced heights, the EGPWS may assume a warning when the flight path is flown exactly as planned. If such a situation ever happens, following EGPWS guidance can be a problem. Now, at what height should the crew level off to accelerate from V2 to VFS? That is an important question. One thing is for sure. The crew cannot use the radio altimeter as a reference to level off because the terrain profile underneath the flight path is not known. So, the crew must base their leveling off on the barometric altimeter. However, a few facts must be borne in mind relative to the use of barometric altimeter. The obstacle heights are geometric altitudes, as opposed to the barometric altimeter, which, as the name says, indicates barometric altitude. This is a very important fact. It means that the barometric altimeter indication coincides with geometric altitude when the atmospheric temperature is standard. It will not coincide with geometric altitude at any temperature other than standard, even if the proper airport QNH is set. The most critical situation is when the ambient temperatures are substantially below standard. Because in such circumstances, if, for example, the altimeter set to QNH indicates an altitude 500 feet above the runway elevation, one may be actually 450 feet geometric above runway elevation. Barometric altimeters are also affected by position errors, as shown on the graphs in the airplane flight manual. As we can see, to cover all these errors, plus some allowance for piloting errors, gusty weather, etc., Embraer recommends that a nice height margin over the obstacles be assumed. The crew can make use of the flight director to reduce workload. So the flight director can be set to altitude hold on reaching the level off altitude and to speed when reaching VFS. The recommended flight standard is, if the aircraft is hand-flown, then the flying pilot calls for the modes and the non-flying pilot sets them and responds. One more important thing about the level-off altitude, also referred to as acceleration altitude. The aircraft must be capable of reaching it with a failed engine and accelerates to VFS without surpassing the 5-minute time limit for the takeoff thrust. So, depending on the weight of the aircraft, runway elevation and temperature, higher acceleration altitudes may not be feasible. There is a chart in the airplane flight manual that shows the maximum level-off height. This chart is exactly the maximum allowable height without surpassing the 5-minute limit. The Embraer provided runway analysis software automatically takes that chart into consideration. So when does the takeoff end? The takeoff ends at 1,500 feet above runway elevation. What if there are obstacles to be overcome after 1,500 feet is passed? The answer is, those obstacles will be cleared on an en route climb. The obstacle clearance analysis must be done based on the en route climb gradient, as published in the airplane flight manual. The speed to clear those obstacles is the en route climb speed, which, in case of the ERJ 145, is incidentally equal to VFS. Now, if the one-engine inoperative takeoff flight path was properly flown, the applicable procedures are carried out, what to do next? Well, it is up to the crew judgment. That is why flight crew members are still necessary. to judge and decide. If an immediate return to the departing airport is necessary, and the aircraft weight is above maximum landing weight, a quick review of the overweight landing technique is advisable. If the aircraft departed a runway that was below landing minima, and an air turnback becomes necessary, the crew must divert to the departing alternates, as they must have briefed prior to takeoff. We hope the information shown in this video can be useful to you, our customer, and help to make your operation safer. We would like to stress once again that there is no replacement to proper training. Not only training to improve skills, but also training to perfect the crew's ability to do decision-making and to prioritize. We wish you happy and safe flying.